Hello and welcome to a demonstration on how to solve quadratics without factoring or the quadratic formula. Suppose we wish to solve the following quadratic equation. Negative 3x squared minus 24x minus 29 is equal to 0. In this particular problem, what I see a lot of students doing is they are trying to isolate x. The apparent misunderstanding, though, is that x squared does not allow for a simple manipulation of just solving for x. So what I happen to see a lot of students doing is they go ahead and isolate the x like they would, and they have x is equal to 3x squared plus 29 divided by negative 24. So this is not exactly solved for x. You have x on both sides of the equal mark. Remember, to isolate x is the goal here, which means that x equals just some kind of number or value that doesn't have x's on the other side. But the issue that I'm going to bring about in this presentation is that if you do happen to do this, then what you are doing is that you are attempting to solve this equation for x. And you're using an idea that is a little bit beyond precalculus, but we're going to talk about, first off, what this idea is. And we are going to basically demonstrate why you do not want to do this when you are solving quadratic equations in a precalculus course. The idea that you're using is known as fixed points or fixed point theory. And what happens is that you are essentially going to generate a sequence of guesses until you converge on one of the answers. So you're going to start with the guess, you're going to substitute that into the equation, and then you're going to use that results and generate a new guess. And you're going to repeat this process until the value of the guesses and the results of the solutions are actually equal. So when I first make a guess of 1 into my equation, I end up with negative 1.083 with the 3 repeating. And I go ahead and plug this new value in, and I get the same equation, and I get negative 1.35503. And I keep repeating this over and over again until you can kind of see down at the bottom that after the 12th iteration, I end up with negative 1.48339. But we know that quadratics have two answers. And we know that because a square root is involved, it is highly likely that the answer is not a rational number. In other words, it cannot be expressed as a ratio of integers. It may still involve that square root, making the result irrational. And essentially what that means is that you would never get exactly at the solution. You could get close, but you'd never actually get there. So using the technique of solving for x, so to speak, and having x on one side and x squared on the other, using this fixed point theory generally leads you to basically a system of guessing where you can get close to an answer through a lot of guesses, but you may actually never get to the exact answer. And in precalculus, we are trying to help you get used to symbolic manipulations and understanding symbols, so we want answers to be exact. So after a few guesses, we can either diverge away from the solution or we do not change the solution. But the problem that we're trying to figure out here is, what are the two exact solutions? So graphically, this is what's happening. You have set up y equal x. That's the green line right here, okay? That's the green line. And what you have now is you have this parabola. That's the other side. So this green line is the left side of that equation. This blue parabola is the right side of that equation. So we see that we have two intersection points. We have one at about negative 1.4833 and another one at about negative 6.5166. And what we're going to establish now is we're going to show why you will not be able to find the second answer if you choose to use this technique for solving. So what we're going to generate here is what's called a cobweb diagram. And in this cobweb diagram, we have an initial guess that's given at x0. And what we do is we take that initial guess and we draw a straight line down to where the curve is. And then we move directly over to where that line y equal x is. And we move down to the curve, and then over to the line, and then to the curve, and then over to the line and to the curve. And as you can see in the chart here, you can see that when I make my initial guess at 1, I end up getting pretty close to the answer, and that after maybe the 10th or 11th iteration, the numbers start pretty much becoming the same. The first 4 digits do anyway. And this tells me that, okay, I have found an approximate solution to the answer, which is about negative 1.483. So here it seems like we are, quote unquote, converging to the answer. And this is with an initial guess of 1. When I make an initial guess at negative 5, as you can see over here in the x sub 0 little blank here, we make a guess at negative 5. I go down to the curve. I move directly over to the line in red. That's the y equal x line again. And then from there, I move up to the curve, then down, then across to the line, then up to the curve, then across to the line. And I basically kind of stair step my way down to this answer. Now, negative 5 was actually pretty close to negative 6, if you remember our answer, our other answer from our previous slides. But again, my table over here is saying that when I started at a guess of negative 5, I'm going to start kind of stepping my way toward that negative 1.483, and therefore I'm still converging to that first answer around this negative 1.483. So what this is essentially saying is that when you make an initial guess for this particular equation, and believe it or not, this is actually quite common in quadratics, is that you end up getting this kind of diagram where you are getting close to one answer with each successive guess. But remember, quadratics have 2 answers, okay? So when we try to guess at the other one, okay, we started our guess at negative 7. But when I did my guess at negative 7, I dropped down to the curve. You always drop to the curve first. And then I moved directly over to the line, and then to the curve, and then to the line, and then to the curve, and then to the line, and keep repeating that. And as you can see on my pattern or my chart over here, you can see that my new guesses are getting me further and further away from that second number. So what this is establishing is that, and you can prove this mathematically, is that what's happening is that when you are getting close to one answer, you might actually start to converge to that answer. But another answer may cause your guesses to move away from it in what we call diverge. So unless you're going to guess right on top of it, you may never actually get to that result. So when you are doing this type of solving technique and you're applying fixed point theory, okay, you may need to have this diagram available to you to see if you're even going to get to the second answer with successive guesses. And that's the point of these cobweb diagrams, is to show whether or not your successive guesses are going to converge to an intersection point or if they're going to diverge to an intersection point. And this is why I do not recommend that you use this type of technique when you solve quadratics in precalculus. You have the quadratic formula, use the quadratic formula. So again, we're not getting to that second solution because the second solution is basically unstable. It's what we call an unstable node. So the first solution we found, that negative 1.4339, that's known as asymptotically stable. So what's happening is that when I guess appropriately, I will eventually step into that particular intersection point. But the other one I can't step into because every time I try to guess near it, either I go toward the negative 1.43 or I end up increasing my values away from that second solution, giving that instability when I try to use this technique. So this is the reason why we don't do such things in pre-calc, is because for the quadratics, we have the quadratic formula that's guaranteed to give us both of the answers. Generating a sequence of values to test for convergence is a calculus concept, not a pre-calculus concept. And if you are steering toward these cobweb diagrams, then you might be able to determine if one of your nodes is stable and the other one is unstable. And if it's unstable, it means that you're never going to get to it. So you would never find it by this technique. It would always diverge away. And because in pre-calc, we're focusing on exact answers, we're focusing on getting the symbolic answer of this technique could only give a numerical approximation. It could never give the exact answer if it were an irrational number. So the arithmetic that's required almost always requires technology, and it doesn't really offer any insights as far as the approach, the solving technique that would be discussed in pre-calculus. Cobweb diagrams are a calculus and beyond topic, not a pre-calculus topic. So if you are interested in cobweb diagrams, here you can go to GeoGebra and do a search for the cobweb plotter. You can just do this as a search engine on Google or Microsoft Edge too. So I thank you for your time and attention. And again, I do not recommend that you do this kind of technique for solving quadratics. I recommend that you just use the quadratic formula and get exact answers in their symbolic form, and then worry about if a decimal approximation is required. Again, thank you for your time.